Let's go to it. So, what are we going to be doing today? We're going to be talking about finding volume of a surface by integrating the area of some sort of cross section. All right, and we're going to basically, the goal is going to be to just figure out where the cross section is happening and then integrate across that distance. All right, so what's going to make today sort of weird is the visual aspect of this, because I think it's sometimes kind of hard to see what's going on sometimes, and being able to see what's going on really does make a difference in terms of like being able to do it, to be honest. So let's go in and we'll see what I mean. All right, lots and lots and lots of words here. But what's really happening is they're giving you sort of the boundary lines of the curve that the cross section is going to sit on. Because they're telling you, okay, so it's it happens from -1 to 1. That's important. And then the cross sections are squares. And the base of the square runs from this semicircle to this semicircle. So first of all, notice that the semicircles that they're talking about are the same except for a negative sign. You know they're just talking about a circle, right? And so imagine for a second, this is going to be difficult to draw the best of times, even worse because I'm just a bad artist. So basically the idea is this circle represents kind of like, imagine like a plate sitting, and then you've got a row, like a whole line of squares just from top to bottom, kind of like, let me get a different color so y'all can see what I'm talking about. Kind of like I'm going to try and draw straight, but you know, it is what it is. And then like it comes up. So imagine like a whole ton of squares on this shape, right? And each one is the size of the circle at that point. So it's gonna sort of it's gonna start out small. The squares are gonna grow because they're keeping with the size of the circle, and then they're gonna shrink back down. And so you sort of get like almost like a really wide shark fin type shape. I don't know if I'm gonna be able to draw this. We'll see, especially on here. Oh, not bad. Kind of like this, and then it comes back in. And there's the base. So that's sort of the shape that we're talking about. And each of these cross sections is a square that sits on that circle. So what I want to do with this is what I really care about is the area of the square. Because if I can figure out the area of the square, I can just integrate from one piece to the other and then I'm done, right? So the cross sections perpendicular to the x-axis between the planes are squares whose bases run from bottom to top here. So imagine the x-axis here. Going up, this distance is radical 1 minus x squared. Going down, I go from 0 to negative radical 1 minus x squared. So the thing of it is, the distance from bottom to top is 2 of these, right? Because they're the same. It's a circle, right? The same circle. So if I want to find the area, the length of one side of this square, the length of the one side of this square is the diameter of this. Well, in this case, the diameter, but like chords of this circle as you move along, right? So what I'm going to be doing anyway is I'm going to be integrating the area of the square, side squared, with respect to our x, from x is -1 to +1, because that's where it goes from, right? From -1 to 1. But I need to get whatever this is. Well, what's the length of the side of the square? It's from here to here, right? It goes a distance of radical 1 minus x squared, and then it goes another distance of radical 1 minus x squared. So one side here is 2 of them. So now I'm going to integrate. That's what this is. So I'm going to square both of these. From -1 to 1. And you can break this up a little bit if you want to. You can distribute, you can pull the 4 out. It doesn't matter which way you go. I would probably distribute if it was me, rewrite it as integral of 4 minus the integral of 4x squared. Just so I didn't have to do it all at once, but you can do it all at once. It's up to you, however your brain works. But we go through and we integrate, and we integrate, and we're evaluating from -1 to 1, right? So let's do that. Let's plug it in. At 1, we get 4 times 1, which is 4, minus 4 divided by 3 times 1 cubed, which is 4 divided by 3. Here we get, at -1, we get -4. And here we get +4/3. So I'm going to distribute that negative sign. I get 4 minus 4/3 plus 4 minus 4/3. 8 minus 8/3, right? And when you do that out, you get 16/3. So what is my final answer? My final answer for this volume is 16/3 units cubed. I don't have any kind of, they're not telling me no inches or anything like that. So the units are just units, just blank units, because we don't have any actual physical measurement. But so that's the basic idea. We figure out the shape. We look and see how our figure is oriented. In this one, the figure is oriented so that the base is what we're looking at, and so we were able to make a very easy equation, and then we integrate, and then we get our answer. That's it. Don't think too hard about this. All right, so now here, same idea, slightly different shape that we're going off of. And it also tells us that instead of it being the base, it's going to be the diagonal of the square that we're looking at now. So basically, imagine what we had before, that picture, that sort of bread loaf thing, but now it's going to be sort of tilted on its side. So y equals -2 radical x to positive 2 radical x. So if we sort of, there we go. So it goes from, I want a different color. Contrast, come on. We can do this. There we go. So here's the first, this is 2 radical x, and this is negative 2 radical x. So now what's happening here is we are looking at our distance here being the diagonal of the square, right? So we're going to have to figure out the length of the side. So the diagonal, and we can just draw a picture, right? The diagonal here is from -2 radical x to 2 radical x. So this one has a length of 4 radical x. And then this is a square diagonal to the side, a 45, 45, 90 triangle, right? So divide by radical 2. And we can simplify this by turning 4 over radical to 2 radical 2 here. So this right here is our side, right? So now, once again, we're talking about integrating the area of a square. Well, a square, once again, side squared, and we're going from 0 to 10 in terms of x. So let's plug this in. Side squared would be, well, 2 squared is 4, radical 2 squared is 2, so that's 8 total. Radical x squared is x. So all we're doing is we're integrating from 0 to 10, 8x dx. Again, don't think hard about this. Integrate 4x squared from 0 to 10, right? So look at what we have. We have 400 as our final answer, right? 10 squared is 100 times 4, and then this 0 part is not going to have any problem here. And so right here, this is our answer. Again, don't overthink too hard. So now we're changing up a couple things. First of all, we're changing up the type of figure that we're working with. Part A, we're working with a triangle, an equilateral triangle. And part B, we're working with another square. For part A, equilateral triangle, so it says from the x-axis to the curve. So it's saying like this, from 0 to whatever the function is. So once again, I need to know what the length of a side is for this in order to do my equilateral triangle thing. Now, we got from 0 to 8 radical sine x, so that's just what we're going to do. It's going to be the length of the side is 8 radical sine x. Now, since we're dealing with a triangle, it's not going to be side squared anymore, right? I think, well, the area of a triangle is 1/2 base times height. We've got the base. Now we just need the height of the equilateral triangle. So for those of you you've got that base right there, the height should be like radical 3 over 2a, right? Because this is 60 degrees. We can do a 30, 60, 90 triangle. Cut this in half. Or you could use the formula for the area of a triangle, like using trig, 1/2 side squared sine theta, and theta is 60. So radical 3 over 2 for sine. So we've got what this is. The area is radical 3 over 4 times side squared. This is something that you could memorize. I remember in high school I had to memorize this at some point for an equilateral triangle. This is only for an equilateral triangle. But then we know what side is. Side is here, so radical 3 over 4 times 8 squared times radical sine squared. And then we can simplify 64 over 4 is 16. So this guy here, the area, 16 radical 3 sine, and that's what we're going to integrate. From where? From 0 to pi. All right, so let's do that. We integrate sine, we get negative cosine. And then we're going to go from 0 to pi. Well, cosine at pi is -1. So we get positive 16 radical 3. And we're going to subtract. Cosine at 0 is +1, so a negative 16 radical 3. Minus a minus, so 16 radical 3 plus 16 radical 3. Well, if I've got 16 sheep and 16 sheep, now I have 32 sheep. So the final area here is 32 radical 3. All right? That's with equilateral bases. So let's do it with square bases. Much easier with the squares because we don't have to do all this extra stuff. Now I sat here and I proved it for you. So in the future, equilateral triangle, you've got the base. You can just jump straight to this formula, radical 3 over 4 side squared. You don't have to show it ever again. It is now just true. Okay, so let's do part B. So now instead of it being an equilateral triangle, this is going to be a square. So forgive the fact that this is still a triangle. But it's going to be the same thing, right? We're integrating just like we did before from 0 to pi. We're integrating the side squared. And what's the side? 8 radical sine theta. So here, for this one, it's just going to be, instead of with the extra radical 3 over 4 silliness in there, it's just going to be 8 squared times radical sine squared. And then we're going to integrate. Integrate sine, we get negative cosine. From 0 to pi. Once again, same thing applies. Cosine at pi is -1, so we've got 64. Cosine at 0 is 1, so we've got -64. 64 minus a -64 is 128. And there you go. Once again, don't try and think too hard about this. Let yourself go back to geometry just for everything in the beginning until you have to take an integral. Literally the only thing that you have to do calculus wise is do the integral of the formula that you create. All right? All right, let's do the next one. So we're going to find a volume bound by a bunch of different lines. So look at the lines that we have. We've got y equals 3x. Let me make a little terrible graph here. Y equals 3x. And then we've got y equals 12. And x equals 0. So we're looking at this area in here. So we've got a bunch of different options for how we want to take care of this part. But remember, what we're trying to work with are these cross sections. So we're talking about these rectangles right here. And what's the base of this rectangle? How big is the distance here? Well, it always ends at 12 and it always starts at y equals 3x, right? So for here, our base, we're going to need a height too, because we're doing a rectangle, base times height, right? Our base is just like what we were doing on Tuesday with the regions, right? 12 minus 3x. And then what's our height? Well, they tell us the height is 10 all the time. So like there's everything we need. So the area, base times height, right? So that's great. We don't have to do much of anything at all. And we're going from 0. Well, y is 12. So if y is 12, what does x have to be right here? 12 is 3 times what? 4. So we're going from 0 to 4. Of this. So let's integrate. We've got 120x minus 15x squared from 0 to 4. Well, the great part about that being 0 is that the back half just goes away because we're plugging in 0 for both of these. So let's just do the 4. 120 times 4 minus x squared. So 4 squared, 16. 16 times 15. Well, what's 16 times 15? Did I not write it down? Is it okay, I'll do it. 16 times 15. I must have been more awake this morning. 30, 80. So 240. Yeah, that seems right. So let's do this, and we end up with a final answer of 240 units cubed. So that's the rectangle with a height of 10. So the next one, they tell us a slightly different story. They tell us that the rectangles, regardless of what the base and the height are, the rectangles always are going to have a perimeter of 60. So what you're going to end up getting is like a really cool shape. It's like an airplane wing. It's actually the same kind of shape that you would have that I have here on this pen clip. It starts out real thin, the rectangles, and then they sort of smush together because the base is getting smaller, so the height has to get bigger, and then it eventually gets out to be like this. So I don't know if you can see from here, sort of like an airplane wing type shape, which is really neat. So let's see how that goes, because it does make some of our calculations more complicated. So once again, we've got to work with our base and our height. Now, the base is going to be the same as it was, 12 minus 3x. And the reason it's going to be the same is because that's still the length of this, right? It's just that now we've got to take into account the fact that the perimeter is 60. 2 base plus 2 height equals 60, right? So we can solve for the height. 60 minus 2 base divided by 2 height. So 30 minus the base. Well, what is that? 30 minus this, right? 30 minus 12 plus 3x. And then subtract, and you get 18 plus 3x. Yeah? 18 plus 3x. So now that we've done that, we're going to integrate. We're going to do base times height. Now, me personally, I'm sitting here like I don't want to have to try to deal with some kind of weird U-substitution. So I am going to FOIL these out. I'm going to multiply base times height, right? So I get 12 times 18 is 216. The two inner terms come out to like negative 18. 3x times 12 is 36x. 18 minus 18 times negative 3x is negative 54. 36 minus 54, that's negative 18x. And then this will be minus 9x squared. Then we're going to integrate. And again, we're going from same thing, 0 to 4. Well, let's do this now. We've got 216x minus 9x squared minus 3x cubed. Yeah, and then from here, once again, we're going from 0 to 4. That is a real godsend, having that 0 down here to, that gets plugged in and it goes away. So we just have to do the times 4. So 216 times 4 minus 9 times 16, which is 144, right? And then 4 cubed, 4 times 4 times 4 is 64, times 3 is 192. And then I do this subtraction problem, and what do I get? I should get 864 minus 336 is 528. Hey, there we go. So the whole thing here is, can we make it to the integral? Because once we make it to the integral, it's the easy part. It's, can we identify what the base is? Can we identify what the height is? If we can do that, everything else is easy. Everything else is easy. All right, next one. So now what's going to happen is we're going to, instead of building our solid and then doing cross sections, we're going to create a solid that's revolved around the x-axis. So this is going to sort of look like a weird stumpy cone. Like, if you can imagine it, like a really wide, flat cone. And then the cross sections are going to be circles, right? So what we need to be able to do is find the radius of this weird stumpy cone, right? Well, isn't the radius just this part, right? Even though it's spinning around, the radius is still half, right? So now the only thing we need to do is take this ignorant thing and put it into slope-intercept form so that we can actually solve this, right? Subtract the 5x, divide by 3. You get that. So this right here, this is our radius. And we're doing circles, right? So we are integrating over pi r squared. And then x goes from 0 to whatever this number is. 1, 2, 3, 4, 5, 6. I can see it right there. If they don't give it to you, you can always plug in 0 as y and solve x equals 6 from 0 to 6, right? Of pi times this squared. So I like to take the pi, put it outside so I don't have to worry about it anymore. You do you. I'm not going to tell you that one way is better than the other. You can leave it on the inside, but I'll show you why I think so. And you could do either U-Substitution or you could FOIL this out. I'm going to use U-Substitution because why not? It's here, right? Let's call U equal to negative 5/3 x plus 10. So that means du is negative 5/3 dx. So that means I can replace this, and in order to cash in the dx, I have to put the opposite of this out here, right? So negative 3/5 out here. So what we have now is, in terms of u, negative 3 pi over 5 times u squared du. And then now we can plug in the limits of the integral as well, right? If x is 0, that means u is going to be 10. If x is 6, that means u is going to be 0. If you want to switch these, then you just turn that negative sign into a positive sign. So you could actually, from 0 to 10, of positive 3 pi over 5 integral of u squared du. And, you'll get the same answer either way because everything will work out. But, some people have a preference. Some people like making it look a certain way. And that's fine. So you got 3 pi over 5. We're going to integrate this. 1/3 u cubed from 0 to 10. Well, this 3 and this 3 are going to cancel out. So let's make life easier. And then u cubed is what? 1,000? Well, what's 1,000 divided by 5? It's 200 pi, right? And there we go. Once again, all we did is we took the area and we integrated it. All we did is we took the area and we integrated it. So notice now, one, they're asking us to rotate around the y-axis. And they've got their function in terms of y instead of in terms of x. So that means when we do this, we're not doing it in terms of x anymore. We're doing it in terms of y. So just watch the way that it's written. Watch the axis that they're telling you. I'll tell you, for this, if they want you to rotate it around the y-axis, you're better off turning it into a function of y if you possibly can. If you cannot, then sometimes it becomes a problem for doing it. So, and we'll talk more about that in a second. So we're going to integrate. Again, this is pi r squared, right? And what's r? It is 4 times the tangent of pi over 4y. And we're going from y is 0 to y is 1. All right, so this one can feel a little tricky, especially if you don't remember some of your your trig identities. So I'm gonna we're squaring this. So this 4 is gonna be squared and come outside. I'm gonna put 16 pi on the outside just to make the inside less ugly, because this is tangent squared, right? Well, I don't know how to integrate tangent squared. No one ever taught me that. How do I fix this? Well, if you remember, tangent squared is secant squared minus 1, right? 1 plus secant equals yeah, 1 minus secant. No, secant minus 1 equals tangent, right? Because 1 plus tangent equals secant. Back from trigonometry. Going all the way back to last year for you guys. A while for me, so you'll have to excuse me. So instead of integrating tangent, I'm going to integrate secant of pi over 4 y minus 1, secant squared minus 1. So when I integrate secant squared, I get tangent, right? Remember we learned that. And when I integrate 1, I get x or y or whatever. So what I'm left with is 16 pi times tangent of this pi over 4y. And then since it's pi over 4 in here, we divide. I'll put the 4 over pi right here. Minus y. And we are going from, what are we going from? 0 to 1. Let's make sure to put the limits on here so that it is not sloppy. And the dy's, because I want to make sure that I'm modeling things appropriately. So now we're going to go from 0 to 1. So we've got 16 pi times this whole thing. Well, what's tangent when y equals 1? Well, when y equals 1, tangent is at pi over 4. And the tangent of pi over 4 is 1. So this is just 4 over pi minus 1, right? And then we're going to subtract at 0. Well, what's tangent at 0? 0 times pi over 4 is 0. Well, tangent at 0 is 0, right? So this all is 0. That is 0. Hey, much better. So now you can leave it here, or you can distribute and get the pi's canceled out in the first part. So you can, that would be the most simple, but you can leave it as this. All right, let's talk about the next one. We're almost done. So in your book and in all the places in the world, this idea is referred to as the washer method, because now instead of getting a circle, we're getting like an annulus, a ring, a washer. But you know, if you remember from geometry, which I guarantee you I've done problems like this before. Really all you're doing if you want to find the area of this part is taking, and in fact I will say I have done this exact thing before. It's just the big one minus the small one. So the outer ring minus the inner ring, because you're punching out the center, right? So what you're really doing is you're doing one radius pi r squared minus another one. You know, so don't overthink this. You're just doing the big circle you sweep out minus the small circle you sweep out. And then it's the exact same problem. So what's the outer radius? Because we're going around the x-axis. What's the outer radius? 2, right? What's the inner radius? Isn't it just this thing? 2 minus radical cosine x. 2 times radical cosine x. You know, and then all we have to do here is just put it here, right? And we're going from where? From negative radical 3 to positive radical 3. What did I just say? Negative pi over 3 to positive pi over 3. Goodness. Pi over 3. And these are going to be the same. So once we put everything together, we're going to be able to just sort of do it all at once, which is nice. So r squared here. So what we have here is integral of 4 pi, right? And then this thing, the square and the radical cancel out. This 2 becomes a 4. So this is 4 I cosine. And then we're going from negative pi over 3 to positive pi over 3. Do I really need this second integral? I don't think I do. Goodbye. And that's, you know, that's pretty much it. Now we're just going to integrate just like we have been. So we got 4 pi x minus 4 pi sine of x. We're going from negative to positive pi over 3. So what is the harder part is the sign, I guess. From negative to positive. Well, this is radical 3 over 2. This is negative radical 3 over 2. So let's do it now. We've got 4 pi times pi over 3 here minus we're doing the top one minus 4 pi times radical 3 over 2. So that's the top. And we can make that like we can simplify this in a second. And then the bottom negative 4 pi times pi over 3 minus negative, so plus 4 pi radical 3 over 2. Right? So, I mean, same thing as we did before. These negatives are going to sort of cancel everything out. We're going to be left with 2 copies of the exact same thing. So this is 4 pi squared over 3. This will be 4 pi squared over 3. So we have 8 pi squared over 3. This will be a negative 2 pi radical 3. This will be a negative 2 pi radical 3. So we've got a negative 4 pi radical 3. And there's our final answer there. Again, don't think about this too hard. These are meant to be easy. If you have just think about it in terms of the 2 circles. If you can think about it in terms of the big radius and the small radius, and then just move on with your life, you don't have to think about it anymore. You are now officially done with all of that. All right, let's do this one now. So find the volume of the solid generated by revolving the region bound by the given curve and lines about the x-axis. So the same thing. So we've got 4x. we've got y equals 4. I've got x equals 0. And we're rotating around the x-axis. So once again, find the two different radii. The big radius is 4, because it's, right? What's the small radius? It's 4x, right? And so now we're going to do this pi r squared minus this pi r squared. Uh, 16x squared, right? Pi r squared minus pi r squared. Don't think too hard. And we're going from where? From x is 0, and then when y is 4, x is going to be 1, right? It's from 0 to 1 on the x. So we've got 16 pi x minus 16 pi over 3 x cubed. So we have 16 pi x minus 16 pi over 3 x cubed. We're going from 0 to 1. Once again, hooray, 0. 0 is our best friend in this case, because I don't want to have to do all that any more than I have to. But then when we plug in 1, we get 16 pi minus 16 pi thirds. So this ends up being 32 pi over 3 units cubed. Hooray! Simple. Don't overthink.